Okay, we start with chapter number 6. So we will consider quantum variables together. Okay, and so this is review some of the points we explained before. So we have a running experiment, and omega is just an outcome. When we do the running experiments, and then we may have used N measurement devices. All right, and so for each outcome, for the first measurement device, we have a device, a measurement result x sub 1 omega, and for the second measurement device, we have the second measurement result x2 omega, etc. Okay, so and we usually ask for the probability that the joint event x1 when x1, x2, up to xn random variables. Okay, so we employ measurement devices such that this n measurement results. Okay, because for each x sub I, it is just a real value function on the sample space, and we impose that a required property, so that x1, x2 up to xn are random variables. Okay, we all know what is the required property before in chapter 4. Okay, so we ask for the probability that this event, the joint event, okay, I'm sorry, occurs when x1, x2 up to xn random variables. Okay, all right, and as we have shown, that when x1, x2 up to xn are random variables, then each parenthesis is an event in the sigma algebra F, right? So this is an event in F, this is an event in F, and this is also an event in F. And so their intersection is also an event in the sigma algebra, so that we can assign the probability for such a joint event. Okay, so this chapter is to describe how can we compute the probabilities of joint event like that. And so we'll talk about joint distribution functions as we have done before for a single random variable. In that, the CDF of a random variable can specify the probability of events described by such a random variable. Okay, and now we will do the similar argument here. Okay, so we start with two random variables. All right, so let x, y be two random variables. Okay, so we already know them. And the joint cumulative distribution function abbreviated as JCDF, okay, of x and y is defined as here, so that it's a function with two variables, and actually is the probability of this joint event. Okay, the way we write it is actually the probability that x intersects. Okay, so the common usually means intersection. Okay, which describes that these two events should occur simultaneously. So this is same as that one, and of course this is the same as x is in this interval, and the y is in this interval. Okay. Or sometimes we describe by the ordered pair. Okay, is in okay. So the ordered pair. So when we put two functions as ordered pair, it is come to a vector function. Okay, so this come to a vector function. Okay, and this is the Cartesian product of two intervals. Okay. Do you have any question about the Cartesian product of two sets? Okay, so no questions. Good. All right. So there are quite a few different ways to describe the same events. Okay, this or that, this one, or when you put them together, then that it is become to a so-called random vector, because it's a vector function, a vector valued function there. Okay, and this is for x, y in R. Okay, so this is called the joint CDF of two random variables x and y. Okay, now so with the joint CDF of two random variables x and y, okay, we can compute. So we can compute the CDF of x and y respectively as follows. Okay. All right, so now the first one is the CDF of random variable capital X, and but its definition is here. Okay, and this is equal to x and y less than infinity. Okay. Because y less than infinity is just the total event. Okay, so this is So this is actually is equal to the total event, the sample space. Okay. Because as we know, y is just a real value function. So any value of this random value should be a real number. Okay, so that's less than infinity here. Okay. So this is that case, and so we have is y less than or equal to y go up to as y go up to infinity. Okay. And in calculus, the meaning of that is to say that for any sequence of y, so you can say for any sequence of y here, okay, we select y sub n, which is a multiple increasing sequence, and go up to infinity. Okay. So the meaning, so I have to indicate that if I omit any sequence version, is actually the meaning of that means that actually for any y sub n sequence, right, goes to infinity, that actually, so this is a multiple increasing sequence of events, and its limit is just equal to this one. Okay, because that you can show that this is equal to okay. So because it's a multiple increasing, okay, as y sub n multiple increasing to infinity, and so the sequence of the event has limit, which is just the union. And you can show this union is actually equal to this event. Okay, we have done such kind of proof several times, so I just omit the detailed proof. Okay. All right, so we have that. Okay. So now by the continuity of probability function, okay, so the f of x, okay, as we know, this is actually equal to which is the limit of n goes to infinity probability of x and y, little yn. So this is the, and so that this is the limit, n goes to infinity, and the joint distribution functions this goes to infinity. And because yn goes to infinity, so that this is equal to, so we call this is, we define, so this is f of x and infinity. Things yn goes as n goes to infinity. Okay. The other way to write the same thing is to show, the other way is that so that infinity. Okay? But the meaning of that means that we can take any sequence yn goes to infinity as n goes to infinity, so that y sub n is a multi-increasing sequence, right? And the limit is infinity. Okay? So the meaning is that if we take any such sequence, then the limit of the sequence of numbers goes to this number. Okay, and similarly, the CDF of random variable capital Y, okay, is the probability that x. Okay, so it's this probability. And the reason is that this event is the total event. Okay, this is the total event. All right, and again, that this is the limit of an increasing sequence of event. So by the continuity, okay, was infinity, and the things similarly go up to the union okay, so we can select yn, xn, okay, go up to infinity as n goes to infinity. So x sub n is a multi-increasing sequence of real numbers, and the limit of x sub n is infinity. Okay, right. So xn is become bigger and bigger, and so as n, so this is a sequence, increasing sequence of event. Okay, and its limit is just their union, and this union is equal to this event. Okay. Okay, and so this is by the continuity of p, right, of the probability function. All right, and so this is the limit, and goes to infinity f of xn and y here. And so this is f of infinity of y. Okay, so we fixed y, and we take the limit. Okay. Any questions? Okay, and so this is actually x goes to infinity and f of x, y. Okay. All right, and f sub x of x and capital F sub capital Y of y are called the marginal CDFs of x and y. Okay. Right. They call marginal because these two CDFs are relative to the joint CDF. Okay. Okay, and so in theory, any joint probability statement about x and y can be answered in terms of their joint CDF. Okay, so let's describe them. But before them, we will describe a special subset in the plane, in the Euclidean plane. Just like intervals, we know intervals in the real line is a very important subset. Okay, right? So a two-cell in the real plane are two. So a real plane is just the real Euclidean space with two dimensions. Okay. It's the Cartesian product I product with J comes to of two intervals I and J in R, i.e. a two-cell X is the set that of number pairs. Okay, so it's a pair, order pair xy in R square, such that the first coordinate x is in I, in the interval I, and the second coordinate y is in the interval j. Okay. So in the picture, okay, all right. So this is the real plane, okay, and we have Cartesian coordinate, right? And in the x-axis, we may have an interval I here. So this is a half open interval, okay? So this is a half closed interval, and we may have right, another interval here, and this is J here. So J is a closed interval. And the Cartesian product would be here. So this is I, Cartesian product with J. And you can see that it's a rectangular area here. Include one side only here. Okay? And they have 3 open sides. Okay? And the reason is because the I is open, is half closed, half open, and J is an open interval. Okay? So this is the okay. So this is a 2-cell. Okay? So any 2-cell is just a rectangular area. And if both intervals are finite, then the 2-cell is a finite rectangle. But if any one of I and J is infinite interval, then of course the corresponding 2-cell would be an infinite rectangle. Okay? Any questions about 2-cell? Okay, so 2-cells are just special types of subset of the real plane, similar to the intervals in the real line. Okay, in the real line. Yeah. Now the event okay, so that the event that the random vector composed of it consistent of x and y. So the random vector is in this 2-cell. All right. So this event is the event. Is the joint event. Intersect. Okay. And usually this is described in this way. Okay. So it's the intersection of the 2 events. And one is described by random variable capital X, the other is described by random variable capital Y. Okay? So that there are either way to write down the event. Sometimes we use random vector to describe the event, or just write down as the intersection of 2 events. Okay. Okay, and so as we described here, the joint CDF, okay, that it can be written by using the random vector. The random vector is in this 2-cell, and you can see this 2-cell is an infinite 2-cell. Okay, so it's an infinite 2-cell. Okay, and you see that as here, this event described by random vector is just described this joint event. Okay. Now, from the definition, all right, so that since there are 8 types of intervals, okay, right? So there are 8 types, right? We have described before. In these 8 types, there are 4 types of finite intervals and 8 types of infinite, semi-infinite intervals. Okay. Other than R itself. Okay? Because R itself is a two-sided, the two, and corresponding to the total event. Okay? So they are okay. So there are 64 types of 2 cells in R square, which are not 1 cells, which are neither R square nor 1 cells in R. Okay. Oh, I have to say that our no such that neither I equal to R nor J equal to R. All right. Which means that I cannot be equal to R and J cannot be equal to R, right? Okay. Right, in particular, all right, so in particular, all right, so in fact, the random vector in any 2 cell can be computed by knowing the joint CDF just by the joint CDF of X and Y. For any 2 cell. Okay, now in particular, right, the probability that xy is in okay. For this special type of two cell, as we know, this is actually right. So these types of two cells can be described just by the joint CDF. How about the other types of two cells? Okay. Now we take several examples to see them. Right. Suppose now this is open, not closed. What happens we have now? And for this is actually the limit n goes to infinity probability that xy is in xn okay. Since right, so we will use the continuity of probability function, and so this is actually because go up to as xn go up to x. Okay, so if xn is selected as a sequence of real number which go up to x, okay, so all xn is on the left hand side and it is multiple increasing, and the limit is x. All right, and so because xn going up, so that these two cells will go up, okay, become bigger and bigger, and their limit, right? So this is actually the limit. Okay, so it's okay. So you can show that this is equal to this one. Okay, and because that we can use the again the continuity of probability function. Okay, so this is the limit, and so this is the limit, and goes to infinity. And as we know, this is the joint CDF, and because so you can see this is x limit xn go up to x, and the f of xn and y. Okay. Right. So this is the meaning that, and so that this is f of x minus and y. Okay. Okay, and you can compute the x. Right, now this time the x is closed, so including this is closed and this is open. So this is again, so we can use that y sub n go up to y, and probability that So we can go up. So we select a sequence yn and going up to y. And so this is limit yn going up to y and f of x yn. So this is f of x and y minus here. Now we use so now the two cell is a Cartesian product of two semi-infinite open interval. Okay, and so this is the limit. We can use xn go up to x probability that xy is in minus infinity of xn. Continue brought out with y here. And this is the limit xn go up to x and the f of xn and y minus. Okay. So we apply this formula here. Okay, so this is closed, this is open, closed, open. Okay, so this is f and y. Okay, and this is f of x minus and y minus. All right, and so please show that. They are all infinite intervals, but so please compute like okay, in so the other parts, well, maybe I compute the so maybe I use that right for I equal to A1, A2, and J equal to B1, B2. Okay. With and so we have that okay. You join union of union okay. So that's draw a picture here. We find A1, A2, so this is X and this is Y. So this is us, the real plane. Okay. And we say here, so this is A1, this is A2. Right? So this illustrates that the case that A1, A2 are finite, but actually you can see that A1 can be minus infinite, okay? So that this is minus infinite is possible, right? So we have this situation. And say this is B1 and the B2, okay? Now, okay, and you can see A1, A2 are closed end, but B1, A2 and B2 are closed end, but A1 and B1 are open end. All right, so we will see that B. So we have okay, closed end, but open end here. Okay, so this is I, which is A1, A2, Cartesian product with B1, B2. Okay, all right, because A2 and B2 are closed ends, so that these two boundaries are included in this rectangle. But because A1 and B1 are open ends, so that these two boundaries are not included. Okay, so this rectangle here. Okay. Now, all right, and the yellow part here. Okay, so the yellow part is that it's A2 cross B2. Okay, so it's very big, right? So including the semi-infinite rectangle. Okay, so this region, a very big region. Okay, and we have to, so that this part, and this is, so the yellow region here is the disjoint union of the rectangle here. Okay, and the union of these two. So what is the union of these two? Well, the union of these two, that on A2 and B1, so A2 and B1, so the green is part, so this green part, it's minus infinity, and A2 times minus infinity and B1. Okay, so it is included both ends. And the other one is here. Okay. So this orange part would be A1 times B2. Okay. But the orange part and the green part has intersection here. Okay, so they have intersections. All right, so I take the unit. So these two infinite rectangle are not disjoint from each other. Okay, so I just take the union only. Okay, so you have that. So we have. Okay, and then we will compute right. Okay. Okay, and so now the okay, and so the probability that xy is in I times j is equal to the probability that xy is in A2 times minus the probability that xy is in A2 B1 union minus A1 times S infinity B2. Okay. And this one, we know this is exactly f of A2 B2. So now we have to compute the probability that the random vector is in this union. But the random vector is in this union. Is in this union. Union. Okay. So by the inclusion-exclusion formula, that this is equal to xy is in plus probability that random vector is in minus the probability that xy is in their intersection intersect with But the intersection of these two, the orange and the green parts, is the yellow part. Okay, so the yellow part is just equal to intersect and the intersect is equal to A1 Cartesian product with B1. Okay. And because the points here, XA1, B1 here. Okay. This point is A2, B2. And this point, it's A2, B1. And this point, it's A1, B2. Okay. Okay. So that this one is equal to minus infinity to A1, Cartesian product with minus infinity to B1. Okay, so this is equal to f of A2, B1 plus f of A1, B2 minus f of A1, B1. Okay. So these three probabilities is actually can be expressed by the joint CDF of x and y. Okay, so this is, so you see this one is A2, B1. And this one is A1, B2, because you can see this is all cross end. Okay. All right, so we put back together so we can see that. So the probability that xy is in I times j is the probability that A1, A2, B1, B2. Okay. And this is equal to f of A2, B2 minus f of A2, B1 minus f of A1, B2 plus f of A1, B1. Okay, so you can see, yeah. So if the ij, if this is, and similarly, okay. So if we want to compute probability that A1 is equal to x, right? So if I is closed interval, and also J is also a closed interval. Okay, the closed interval here. Then you can write, because this is closed, and A2, so A2 already closed here, but now A1, A2, in here we have open, right? But now it's closed. So this is A2, B2, minus f of that A2, but B1 minus f of A1 minus and the B2 plus f of A1 minus and the B1 minus. Okay. And so with similar argument, we can compute P of xy for other types of two cells. Okay, so the previous calculation just give you the idea that as long as we have the joint CDF of two random variables, then we can compute, all right? We can compute a joint probability statement related to random variable x and y. So basically, we can do that. Right. All right, so this is the general case, right? For x and y are general random variables. Now we will consider two special cases. The first special case is that when x and y are discrete. Okay? So when they are discrete random variables, and take on one of the values a sub I and b sub j, respectively. Right? So of course, a sub I, there are countably many a sub I, and also we have countably many b sub j's, okay, as we define discrete random variables before. Right? We define joint probability mass function abbreviated as JPMF of x and y as here. So the P xy is defined to be the probability that x equal to is defined to be x equal to AI, y equal to bj. Okay. When x equal to AI and y equal to bj, and the 0 otherwise. Okay, so we define the joint PMF. Okay, and so the function is a function on two real variables, x and y. So x can be any real numbers, y can be any real numbers. But the joint PMF has non-zero value only when x equal to AI and y equal to bj. Okay. The PMFs P and of x and y can be computed from their joint PMF as follows. First of all, we compute the value of PMF when x equal to AI. Then we know this is by definition. Okay. And so this is probability. Okay, intersect the union, disjoint union J. Okay. And we know this is equal to the total event, right? Because P sub J are possible values of capital Y, so that they are disjoint events. Okay. And the union is just the total event. Okay. And so this is the probability that disjoint union of J and x equal to AI, y equal to Bj. Okay. And so this is summation by the countable activity of probability function. Okay. So this is J, summation J, P, AI, and Bj. And for all x not equal to AI, we know that P x, okay, and again, so this is okay. Yeah, because the x is not equal to any AI. Maybe I will use x not in here. All right, and similarly, little p y bj will be that y equal to bj. Will be that disjoint union I x equal to ai intersect. Okay. So this is probability that ui summation I probability x equal to ai y equal to bj summation I p ai and bj. So that the bj we can take. And for all y not in bj, little y, probability of with little y again. Okay, it's here, and the probability that the joint union x equal to ai, y equal to little y, summation I, x equal to ai, capital Y equal to little y. Okay. And because y is not in any B subject, so that we have summation of I and zeros, and so the value is zeros, as we know. Okay. So here, little p and little p capital Y are called the marginal, all right, so the marginal PMF of x and y. Okay, and here, the joint PMF, so how do we do the, so this is actually equal to probability that x equal to x, y equal to y. Maybe I write here. So this is equal to probability that x equal to x, y equal to y, right? So the joint PMF is actually this joint probability. Okay. And so that this is probability that x okay? So it's this in this rectangle. And recall here. So what we have, in terms of the joint CDF, so which is fxy, right? And the minus f of x, y minus f of x minus y, plus f of x minus y minus. Okay, so we can obtain the joint PMF of two discrete random variables by their corresponding joint CDF. Okay, by their joint CDF here. Okay, if need, we apply this formula here. And so that this is the way we can express the joint PMF by the joint CDF. How about to express the joint CDF by joint PMF? Okay. Okay, and so so we know that this is probability. Okay, so that this is equal to y is in Cartesian product. Oh. Okay, and so that is equal to probability that xy equal to ai bj such that probability that x equal to ai and y equal to bj. Okay, and union, so it would be the disjoint union x equal to ai, y equal to bj, such that ai bj is in So this is a summation that ai b sub j is contained in of the big P. Big P. Okay, so this is summation that AI is this x and the BJ should. Okay, so you should satisfy, and P of AI BJ. So you sum over all PI AJ pair such that A sub I is less than or equal to X and the B sub I is less than or equal to Y. Okay. Right. So the joint CDF can be computed by this formula. Okay. Okay. So if we know the joint PMF, we can compute the joint CDF. Okay, and so that the joint PMF give us the total information about the distribution of the two discrete random variables x and y. Okay, and so it is much more easier to compute the joint PMF of two discrete random variables. Okay, it is much more easier to that. Okay. Okay. So usually, the distribution of two discrete random variables will be described by their joint PMF instead of their joint CDF. Okay? Even though we know how to compute their joint CDF from their joint PMF. Okay? On the other hand, if you know the joint CDF of two discrete random variables, then you can use this formula to compute their joint PMF. Okay? But as you can see, it will involve the left limit, okay, of the joint CDF of these two discrete random variables. Okay. So this is the first case that the two random variables we consider as our discrete random variable. The other special case is we define here. Two random variables, x and y, okay, are called jointly absolute continuous. If there exists a non-negative and integrable function f of xy, okay, on the real plane at square. So suppose we have a non-negative, so the value of the two variables of the function of two variables are non-negative and they are integrable on the real plane. I.e., non-negative means that f of xy will be equal to 0 for all xy in R square, and their double integral is finite. Okay, so that this means that they are non-negative, and this means that they are the function f of xy is integrable. Okay, such that for any two cell I Cartesian product with J on R2 in R2, we have that the probability that the random vector is in the two cell, okay, is equal to the double integral of the f of xy over these two cells. Okay, so this must be true for any two cells. Must be true for any two cells. All right? Any such a function f of xy is called a joint PDF, a joint probability, a joint probability density function. So abbreviated as joint PDF of random variables x and y. Okay. Okay, so to check that two random variables x and y are jointly absolutely continuous, we have to find a joint PDF for these two random variables. Means that we have to find non-negative functions on the real plane, right, which is integrable over the real plane. Okay, so the double integral of this kernel, of this integrand, should be finite. Okay, and you have to verify that for any two cells, this probability is equal to this double integral over the two cells. All right, and we have to know that because the integrand is non-negative and integrable, since f of xy is non-negative and integrable over R square. Okay. It's non-negative and integrable over any two cell. Okay. And the double integral can be evaluated by iterative integral. All right. And so, and then the double integral, maybe this is too small. I will write here. Can be integrate. Okay, so you can evaluate the integral first over y and then over x, or you can right, by Probability theorem. Okay. So if the integrand is non-negative and integrable, then Probability theorem tells us that the double integral can be do it iteratively. Okay. Okay. And the integration And this integration is equal to that A1, A2, B1, B2. Okay. And this iterative integration okay, when I is the 4 taps of finite okay closed interval, and the J is because it's over the dx and dy, because it's the integrator is linear. Okay, so all right, and we make several remarks. First of all, we know the total event has probability 1, okay? And so that this is equal to the random vector is in R2, okay? All right, so this event is just a total event. And so the double integral of any joint PDF over the whole real plane should be equal to 1. Okay? This is the necessary condition for a joint PDF. Okay? A necessary condition. If we specify that the random variable x has a specific value, say a, okay, and y is in any interval j. J can be the whole real line anyway. So if this is the case, now we know that this is equal to that okay. So by the formula we have, but this integral is 0. 0, so this is 0. Okay? Because over a point that this is 0. And similarly, if y is equal to a specific value b, then we know that so again this is 0. The first one is very important to verify that a non-negative and integrable function f of xy on R square is a join PDF of random variables x and y. Okay, it is sufficient. So it's sufficient to check that so it's sufficient to check that the joint CDF of x and y okay. So this is probability that xy okay, is equal to okay, xy is contained in here. Okay. And is equal to okay, or you can evaluate the double integral the other way. Okay. Okay, so it is sufficient to just check that we can compute the joint CDF in terms of this double integral of this non-negative and integrable function f of xy over these two cells. Okay. Any questions up here? Okay. Okay, so for two jointly absolutely continuous functions, the joint CDF can be computed by the double integral of a joint PDF over a specific two cells. Okay, now we talk about Borel set in the real lines. Now we extend the concept of Borel set in the real plane. Now the smallest sigma algebra, which contains all two cells I Cartesian product with J in R square is called the Borel sigma algebra in R square. On R square and denoted as square B square. Okay. So starting with two cells, okay, we can do complement, union, counterpart union and countable many intersections. All right, and then so we can form a sigma algebra, okay? And any member in square B square is called a Borel set in R square. Okay. So now we give a proposition 6.1.8. Two real valued functions x and y on the sample space x are random variables, okay? If and only if okay, if only if that this is subset of the sample space defined by a Borel set C, okay, so that this is omega such that okay, it's in C, okay, so which is just the subset, okay, such that the value of x and y together is a point in C. So okay, so this is an event in the sigma F for any Borel set C in R square. Okay. Okay, so if we want to justify two real value function to be random variables, we can look at subset of the sample space, okay, such that it defined an event in the sigma algebra F. Okay, for any Borel set in R2. Borel set in R2, sometimes we call two-dimensional Borel set. Okay, two-dimensional Borel set. Okay, and the proposition is important to see that we can assign probability, okay, for any event described by x and y jointly. Okay, so we can define an event, okay, and it's described jointly by this random vector, a function, okay, a vector function, and which is in a two-dimensional Borel set. And it can be shown that if okay, so the proof I just omitted. Okay. It can be shown that if two random variables, x and y, are jointly absolutely continuous with a joint PDF f of x, y. Then, so if we know x and y has a joint PDF, then for any Fourier set C in R square, the probability of this event, okay, can be evaluated by the double integral of the joint PDF over C. Okay, over C here. We may have a question. If x and y are jointly, absolutely continuous with a joint PDF fxy. Okay? So suppose x and y absolutely continuous. So we ask, so when x and y are jointly absolutely continuous, it's a natural question to ask, are x and y absolutely continuous? Right? The answer is yes. Okay. Now we explain why the answer is yes. All right. So we compute the CDF of capital X. So we know this is okay, and this is actually okay. All right, and so that this is equal to right here. Now define Then f of is non-negative, and the integral over R with oh, by the way, I have to use okay. So that is a PDF of x, and x is absolutely continuous. All right, so we find a PDF. And as we know in chapter 5, okay, to justify that a non-negative integrable function to be a PDF, we just show that it's CDF, right? Can be evaluated in this way. Okay, so we actually directly find a PDF. Okay, and similarly, if we want to find the CDF of quantum variable capital Y, so this is equal to, so that would be the x here, and then we know that this one, and by defining the B which is non-negative and the integrable over R Y is absolute continuous with a PDF. Okay. Okay. Right. The two functions and are called the marginal PDF of x and y. From the joint PDF. F of xy. Okay. With different joint PDF, you may have different marginal PDFs. Okay, and we know that if two random variables are joined to the absolute continuous, there are infinitely many joint PDFs. Okay. Any questions? Okay, so I stop here.